We're always on the lookout for breakthroughs, aren't we? Especially when it comes to clean energy.
Absolutely. Powering the world sustainably is the big challenge.
And today, we're diving into something really significant, a major step forward.
You're talking about the new electromagnet system.
Exactly. The world's largest superconducting electromagnet system, it's just been completed.
Right, for ITER, the International Thermonuclear Experimental Reactor.
That's the one. Down in southern France, it's this huge global collaboration, over 30 nations?
All working together to try and prove that fusion energy is actually viable, practical.
And this magnet system, sounds like it's pretty central to the whole thing.
Oh, absolutely fundamental. Its completion is a massive milestone.
Okay, so our mission for this deep dive, let's unpack why this is such a big deal. Why this electromagnet system is so monumental for, sustainable energy.
Sounds good. It's a complex piece of kit, but the implications are huge.
So let's start there. What exactly has been finished? What's the achievement?
Well, they've successfully assembled ITER's pulsed superconducting electromagnet system. And like you said, it's the biggest, the most powerful one ever put together.
Pulse superconducting, okay.
Yeah. And it's basically the heart of ITER's tokamak. That's the machine designed for the fusion reactions.
Big tokamak, right. And
Right.
superconducting means less energy loss.
Exactly. These huge magnets can carry enormous currents with almost no resistance, no energy wasted as heat. You need that for the incredibly strong magnetic fields fusion requires.
Got it. Now, for listeners, maybe especially those preparing for the UPSC exams and thinking about energy security, big science projects remind us what ITER is trying to achieve with this tokamak.
Good point. For UPSC aspirants, this connects directly. ITER's core mission is to demonstrate scientifically and technologically that fusion power can work.
To show it's viable on a large scale.
Yes. To prove we can harness the same energy process that powers the sun, but do it here on Earth. It could be, a game changer for long-term energy needs. Clean, abundant energy.
It's incredibly ambitious. And the ITER Director General, Pietro Barabaschi, he pointed out something interesting.
What was that?
He said, it's not just the technical difficulty, which is immense, obviously, but also the international cooperation, keeping 30-plus nations working together through all the political shifts. That's quite something.
That really speaks volumes, doesn't it? The commitment involved.
So let's talk about the core component, the central solenoid. That's the main piece.
It is the absolute linchpin. It weighs, get this, 3,000 tons, just that one component.
3,000 tons. And it wasn't built on site.
No, and this is another key point about the collaboration. It was built and then tested really thoroughly in the U.S. And then shipped all the way to France. The logistics alone are, mind-boggling.
So what's its main job, this giant solenoid?
Its primary function is to start the whole process. It initiates a powerful current in the plasma.
The superheated gas.
Exactly. And then, critically, it helps confine that plasma within the tokamak, keeps it stable and away from the walls. It's really the driver.
Okay, so it's the driver, but it needs support. It doesn't work alone.
Correct. It works hand in hand with 6 other magnets. These are ring-shaped, called colloidal field magnets.
And where do they come from? More international teamwork?
You guessed it. These were built and delivered by Russia, Europe, and China.
Really showcases the global effort.
Absolutely. And when you put the central solenoid and these 6 colloidal field magnets together, that's your entire pulsed magnet system, still weighing in at that massive 3,000 tons.
Incredible scale. Okay, let's get into the science a bit more. For, anyone needing the details for exam prep or just plain curiosity, how does this magnetic system actually make fusion happen inside ITER?
Right. The simplest analogy is the sun, right? We're trying to replicate that process.
Makes sense.
So they inject hydrogen isotopes, specifically deuterium and tritium, into the tokamak chamber.
Right.
Then the electromagnet system, driven by the central solenoid, induces a massive electrical current in those gases.
And that heats them up.
Heats them up incredibly fast and hot. So hot that the electrons are stripped from the atoms, and you get plasma, this superheated, electrically charged gas.
Okay, plasma formed. But it's unbelievably hot. How do the magnets handle that?
That's their main job. The powerful magnetic fields generated by the whole system, the solenoid, the colloidal field magnets, they act like an invisible container.
A magnetic bottle, sort of.
Exactly. A magnetic bottle that confines the plasma, shapes it, and crucially keeps it from touching the reactor walls.
Because if it touched the
It
walls...
would instantly cool down, the fusion reaction would stop, and you could damage the machine.
Makes sense. And the temperatures, we're talking extreme, right?
Oh, beyond extreme.
Yeah.
Around 150 million degrees Celsius.
Wait, say that again?
150 million degrees Celsius.
That's, what, 10 times hotter than the core of the sun?
Roughly, yes. 10 times hotter. It's only at those kinds of temperatures that the hydrogen nuclei have enough energy to overcome their mutual repulsion and actually fuse together.
Mind-blowing temperatures. So when they fuse, that's where the energy comes from.
Precisely. At that heat, the nuclei are moving incredibly fast. When they collide and fuse, they form a heavier nucleus, like helium. But the key thing is, a tiny amount of their mass is converted directly into a huge amount of energy.
Einstein's EMC squared in action.
Basically, yes. Mostly released as heat energy, ITER puts it simply. Atomic nuclei combine and fuse, releasing massive heat.
And the whole point, the grand goal, is to show that this heat can be used to generate electricity reliably.
That's the ultimate aim. To prove fusion as a practical energy source for the future, and the numbers they're aiming for are pretty impressive.
What are we talking about in terms of output versus input?
They're targeting 500 megawatts of fusion power output from just 50 megawatts of input heating power.
Whoa, that's a 10-fold energy gain. Q10, they call it.
Exactly, a gain factor of 10. That's not just a small improvement, it's the kind of gain you need to start thinking about actual power plants.
That really changes the game. And there was something about a burning plasma. What does that mean?
Ah, yes, that's really exciting for the future. A burning plasma is essentially one where the fusion reactions themselves generate enough heat to keep the plasma hot.
So it becomes self-sustaining.
Largely self-heating, yes. The high-energy particles produced by fusion collide with the surrounding plasma, keeping it at that extreme temperature without needing as much external heating. It's a crucial step towards a power plant that can run continuously.
So ITER's design, aiming for Q10 and exploring burning plasma,
Yeah.
it really is a major step towards potentially clean, sustainable power.
No doubt about it. A huge stride.
We've touched on the science and engineering, which is staggering, but the international cooperation aspect keeps coming up. It's not just one country doing this.
And that's so important to grasp, especially thinking about global governance and collaboration, relevant again for UPSC folks. ITER is a massive testament to what happens when countries work together on huge challenges.
Over 30 nations?
Yes, each contributing vital pieces. Expertise, technology, actual hardware. It's not just a science project, it's a diplomatic one too. A shared goal that kind of transcends typical national interests.
Can you give a few more examples? We mentioned the U.S. with the central solenoid, Russia, China, Europe with the colloidal magnets.
Sure. Then you have Japan and South Korea heavily involved in building the complex vacuum vessel that contains the plasma. India's contributing crucial components like the cryostat and shielding.
So it's a truly integrated global effort.
Completely. Everyone bringing their strengths to the table for this common goal, making fusion power a reality.
It really reinforces what Director General Barabashi said about resilience, surviving geopolitical shifts.
Exactly. And his quote about ITER embodying hope, showing that, a sustainable energy future and peaceful cooperation aren't mutually exclusive goals. They can go together.
It's a powerful message. Okay, this has been fascinating. Pulling it back for our listeners, especially those maybe studying for exams like the UPSC, why is keeping track of ITER so relevant?
Well, looking at the UPSC syllabus, ITER hits multiple points. Obviously, science and technology, it's cutting-edge energy research.
Right.
Then, international relations, it's a huge case study in multinational collaboration on a massive scale. Energy security fusion promises a potentially limitless clean source, changing the whole security dynamic.
Environmental concerns, too.
Definitely. Environment, climate change. Fusion offers a potential solution without carbon emissions or long-lived radioactive waste like fission. So understanding the tech, the collaboration, the potential impact, it cuts across several key areas of the syllabus, prelims and mains.
Good summary. So if we boil down our deep dive today, the main takeaway.
I'd say the completion of this massive superconducting electromagnet system is a really pivotal moment. It's not the end goal, but it's a critical hurdle cleared on the path to demonstrating fusion power.
A huge engineering success and a symbol of global teamwork.
Absolutely, a blend of scientific achievement and international partnership.
Okay, so here's something for you, our listener, to think about. If, and it's still an if, but if commercial fusion power does become a reality down the line, what happens then? What are the really deep long-term societal shifts, geopolitical changes? How does the world look different with potentially abundant clean energy? That's definitely food for thought.
Indeed it is. Major implications.
All right, that wraps up our deep dive on this ITER milestone. If you found this useful maybe for your studies, maybe just for staying informed, please do hit like, subscribe, maybe leave a comment if you have more questions. We do try to check those.
Yep, always good to hear from you.
The information we discussed today came primarily from reports on dailygalaxy.com.
A good source for this kind of cutting-edge science news.
Join us next time as we tackle another key topic, making waves. Thanks for listening.